Well, we have a brand new speaker ready to go. Michael, I just want you not to get confused by seeing me as your chair. This is not Warsaw. We have 15, not 90 minutes for your talk. Take it away.
Okay, thank you very much. And thanks as well to the organizers for the opportunity to speak here. As you can see, I'm going to be telling you about Newlander-Nirenberg. So this is to do with complex geometry, but in B geometry. So this is joint work with myself and with Tatiana Baron, who's at Western University, where I also am. And depending on how kind of far I get into these slides, I may also sort of connect it to some work earlier from my PhD thesis and sort of say where I hope to kind of connect these ideas. Okay. So B geometry, what is B geometry? Also known as log geometry. There's sort of a spirited debate about which is the better terminology between the two. My sense is that if you like, if you're a fan of algebraic geometry, you should talk about log geometry. And if you're a fan of Richard Melrose, then you say B geometry. So I don't know, I'm trying to be a sort of a non-combatant, so I just alternate between the two terminologies if I have to talk about these things. But it's a fairly simple idea. So you're working on a manifold M, which has embedded in it a closed hypersurface Z. The idea is you can consider the vector fields on M, which are tangent to Z. And this is a projective module with the same sort of rank as just considering all vector fields on M. And Sarah Swan tells you that it's a projective module, and it corresponds to, it arises as sections of some vector bundle. And that vector bundle has a name, which in this talk is the B tangent bundle. So this is the vector bundle whose sections are not all vector fields, but vector fields that are tangent to Z. And the game in B geometry is so much of geometry just refers to the tangent bundle. So you can sort of do whatever geometry you like with this replacement for the tangent bundle. So if you want to do sort of Riemannian B geometry, you put your metric on this. And if you want to do sort of symplectic B geometry, which many people have studied, you put your form on, I guess, the dual of this. And we'll be talking about complex B geometry. So we can talk about complex structures using the tangent bundle, and we'll replace it with this gadget. Here's an example. So what sort of do you need to span all vector fields that are tangent to, say, the y-axis here? You need some Euler type vector field escaping the y-axis, and you need a parallel direction you can move. There's a little more to it. It's not just a vector bundle. It's actually a Lie algebroid, which is mapping to the standard tangent bundle. And in fact, those things are indistinguishable. So if you restrict away from Z, I guess I'm calling it, then this kind of sort of anchor map, if you like this terminology, is an isomorphism. So you can't distinguish those two vector bundles. They're canonically isomorphic if you stay away from this hypersurface. So let me remind you a definition of complex manifold. So you complexify the tangent bundle, and a complex structure is specified by this sort of involutive splitting. So involutive is like the Frobenius theorem involutive, so it means closed under the bracket. This is a little bit of linear algebra away from the sort of J operator definition, if you like that instead. But complex structure is specified by a subbundle of the complexified tangent bundle. And the model example is you're working on R2n, and this subbundle is cut out by these sort of standard complex derivatives, d by d zj bar. And the Newlander-Nirenberg theorem says this definition, which a priori doesn't mention charts anywhere, is kind of equivalent to the chart definition. So if you're on some complex manifold, locally you can find coordinates, where this subbundle is just cut out by what I wrote above. So this theorem is either sort of a truism if you define complex manifolds by saying a complex manifold is covered by holomorphic charts such that blah, 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 then this is just a tautology. But if you define complex manifold like I did above, then this is a theorem. The Newlander-Nirenberg theorem is sort of the tool that lets you get the charts just from this sort of integrability hypothesis. This isn't involutive. Okay. Okay, so complex B structure, probably defined by multiple people, but I'll attribute it here to Mendoza, 2014, considered a complex B manifold to be the exact same thing. If I flip back and forth, I don't know which button to press, but these definitions would sort of change very little. Just the word B gets put in a few places. So it's the same definition. And the integrability hypothesis uses, I guess, the fact that the B tangent bundle is an algebroid. So you can bracket vector fields that are tangent to Z. They remain tangent to Z. The issue with a definition like this, or a lot of the definitions you can do where you just formally replace tangent bundle by B tangent bundle, is it still geometry, right? Like the reason we like Riemannian geometry is because you have things like locally you can write the Taylor series of the metric in terms of curvature or something like that. Or symplectic geometry, you have the Darboux theorem, which says sort of locally you can find model space. Complex geometry is the same. You have one local model which has sort of all the geometry in it. So even though formally there's some integrability hypothesis here, where are the charts, you know? Like what does a B complex manifold look like locally? It's not clear at all from this definition. I just formally replaced the tangent bundle with the B tangent bundle. By the way, this is probably important to mention. So because of what I said before, that the B tangent bundle and tangent bundle are just identical if you stay away from Z, a B complex structure determines a usual complex structure on the complement. So if you stay away from Z, this sort of upper half plane, I guess, in this picture is an ordinary complex manifold. And actually, you could kind of take that approach. You could say, I'm studying complex structures on the complement of Z, which do not extend to Z. In fact, there's not a complex structure defined everywhere, just on M take away Z. But I have specific assumptions about the way that complex structure sort of degenerates when I hit Z. So it becomes kind of, it has some sort of cylindrical asymptotics or something. That would be like another way to kind of set this theory up. There's a specific sort of type of degeneracy that happens to the complex structure that's living here when you get towards Z. Sort of logarithmic, maybe I should say the word log more, so I'm not taking sides. But in this talk, B is the name of the game. Okay. And there is a model example. There's sort of a maximally dumb example that you can come up with. So you just add, okay, so now I've gone to R2n plus 2. Again, I'm taking the sort of y-axis as my hypersurface. And the subbundle is cut out by the usual complex derivatives, but now I also have this weird one which I put a b in front of to sort of ostracize it from its peers. So it has, you'll notice, this Euler-like sort of part to it. Any questions? So this is the dumbest example, and you sort of hope maybe that it works the way it worked in complex world, that everything just looks like this local model, and then you can come up with a counterpart to this definition that is like charts. So there's sort of a B holomorphic chart, and you have B holomorphic transition maps, whatever those are, and locally everything looks like that. That's what you sort of would maybe hope. Okay, yeah. Well, it's not like a complex hypersurface, it's a real hypersurface. So there's just sort of, you just need a real valued function to cut out this hypersurface Z. So x0, if you want, is sort of a defining function. And that's why x0, for Z. And that's why x0 is sort of more privileged than y0 here. But I mean, these are just labels, so yeah. Okie doke. so what's next? So I need to acknowledge that Mendoza, whose name I put earlier, really did think about this. And so I attributed the definition to Mendoza, and he sort of did a systematic study of what you would call the B-Dolbeau complex. And I'll leave it to your imagination what that might be. So he analyzed this systematically and proved, sort of using this analysis, almost the theorem that you might want to see, up to sort of some deformation terms that I won't write down, but there's like some error here. So it's not, he's not quite finding the charts that eliminate some garbage here. These are vector fields that vanish on Z to infinite order. So to just put everything on this slide in a slogan, there are no, he proved that there are no sort of formal local invariants at the boundary. So maybe there's not just a local model, but sort of up to Taylor series that you can't, up to stuff you can't capture in Taylor series, there's sort of no local invariance. Anything else I should say? So what's involved? There are some names here. So it's using some classical stuff, hypoanalytic coordinates that you sort of find in work of people like Hormander, actually Newlander-Nirenberg themselves, and Kleb. Okay. So maybe I better move past this slide. It looks kind of, I'm getting a little spooked by it. So, also I would like to ask, when do I stop? Okay, let's continue. So what we did is get rid of those error terms. Tatiana and I proved that it is the case that there is just this one local model. Oh, and then this is a typo. So what we proved in a slogan is that there are no local invariants. Oh, no, this is correct. Sorry. The word formal is gone. Okay, so I thought there was a typo, but yes, this is correct. So I'll just, I don't have a lot of time, obviously, to get into some details, but let me just so some of you probably instinctively see what the issues are. The main issue is the non-ellipticity of this operator, BD bar operator, which means that the sort of B-Dolbeau operator is also non-elliptic. This sort of model operator has solutions, so you can check x e to the iy is in the kernel of that operator. But because it's not elliptic, it doesn't a priori allow you to do things like deform that operator. So if you add something to it, if you deform an elliptic operator, it's sort of still elliptic, and you still have existence theory that you can apply, but that doesn't work here. And there's a little more to it than that, because so in Newlander-Nirenberg, you sort of just want to find a supply of holomorphic functions to get charts. But that's not quite enough here, because actually the solutions to this operator, they're sort of like constant along Z. You kind of see that with this one. And they're not really going to give you charts. So they may provide you charts, and we show that they do, but you need to do more further constructions. So there's sort of two steps. Show that you have enough B holomorphic functions, and then somehow use those to manufacture coordinate systems. And here's a trick, which I'm sure we cannot really absorb here, but there's something very nice about, so this polar coordinate change will transform what I called the BD bar operator to the standard one with like a factor in front. And using that trick, you can sort of relate some things to other things. I wanted to talk about this a little more than I will. And I think, given the time, that's probably a good place to stop. So, so let's stop.
Thank you so much.